Thank you, Simon. It's very exciting to be here and to see old friends and meet new people. I realized that when I sent the title, Cosmic Consistency over 12 billion years, I didn't have a question mark, but now I've added a question mark. So that tells you a little bit about how fast things change in the field, or at least in my head. So I want to talk to you a little bit about just using the universe to do an experiment that's a little bit strange. It's kind of a retroactive experiment, right? Usually when you think of an experiment, you try to make a prediction and then go and do a new tests that prediction. But with the universe, you just have one realization, and you have to look up at the sky and think of ways to check for consistency. But we have a lot of volume in the universe, right? The universe is really big, and we can ask some questions by looking at certain epochs of the universe and testing the predictions that you make based on a model you build on the early universe and extrapolating that to the late universe, right? So that's really the main theme here when I talk about cosmic consistency over 12 billion years. For context, to prove, as you all know, the universe is 13.8 billion years. As Simon mentioned, I don't work on all of the questions, not everything related to the late universe, things like supernovae, using them as distance indicators. But with the cosmic microwave background and large-scale structure, at least over the first 12 billion years, you can make some really good measurements and predictions, and then tests of those predictions. And the experiments that I'm going to focus on are two millimeter wavelength or microwave frequency experiments, so the observatories. One is the Atacama Cosmology Telescope. So you'll often hear me saying ACT, which is the Atacama Cosmology Telescope. It was decommissioned a couple of years ago. And its successor built at the same site, the Simons Observatory, which is one of the experiments that ASU is heavily involved in with as well, right? So just to set the context here again, you are here today. The universe is 13.8 billion years old, and light travels at a finite speed. So as you look farther out, you're going to see older objects, right? Because light takes time to travel to you. In particular, galaxies are relatively new in the history of the universe. And the eventual fog that you reach, the thing beyond which you can't get light signals from, is the cosmic microwave background. And I'll expand on that a little bit more. So it's the oldest light that we have direct access to. If you're able to build really good neutrino detectors, you can go back all the way to the first few minutes, whereas the cosmic microwave background is giving you a snapshot of things that happened around 380,000 years after the Big Bang. Another way to orient ourselves here is to just think about the big picture expanding universe history here. Lots of evidence for an expanding universe for more than a century, right? And through this expansion, the universe goes through certain phase transitions, right? So right now we're at a point where we have stars and galaxy clusters, but that wasn't always the case, right? So if you go back earlier, you're going to be in a hotter and denser universe. If you go back all the way close to the Big Bang, you're in a plasma state. Much closer to the Big Bang, you go through several other phase transitions that particle physicists like to explore. But just think about the first 380,000 years, the universe is completely opaque to radiation. So you have photons that are bouncing off electrons and photons continuously. And as the universe expands and cools, you can form neutral hydrogen atoms, right? So you're below the ionization energy of the hydrogen atom. And the universe suddenly becomes transparent. And the photons that were bouncing off the electrons and photons earlier on in the universe suddenly become free to travel and propagate throughout the universe, and that forms this cosmic microwave background, this fog that eventually we're able to access. Now that you have neutral hydrogen atoms, the universe goes through a phase where there hasn't been enough time for things to grow under gravity to form things like stars. So you're really in a neutral hydrogen phase that doesn't really glow that much. So these dark ages over here. And eventually, you form structures. You start to form the first stars. And the first stars are going to start putting out UV radiation at high energy. And they'll start to re-ionize the universe eventually. And a lot of people here, of course, are experts on reionization. once you have galaxies, once you have stars, you have galaxies forming. Eventually, those galaxies cluster, and you have structure forming late in the universe. Now, the great thing about this field is that there's a huge variety of experiments that access and probe these many different epochs of the universe. So at first glance, you would think that microwave experiments, like the one that I'm going to talk about, are really just exploring this very early universe, the 380,000 years since the Big Bang. Planck, ACT, the South Pole Telescope, another telescope close to the South Pole, and the Simons Observatory. For the dark ages and the epoch of reionization, there's a number of radio observatories that are either operating now or will be soon that can probe those epochs. They're much larger volumes of the universe as well. And then later in the universe, when you're looking at galaxies, there's many, many other experiments that have or will continue to collect lots of data that map out the structure in the universe later in the universe. Now, one of the things I want to get across in this talk is the idea that cosmic microwave background, which you usually think of as a snapshot of the early universe, those are the primary anisotropies in the early universe, the structure that you see in the early universe. But as those photons propagate through the universe, you're going to pick up some secondary anisotropies because they eventually are propagating through a universe that evolves with time. And the CMB photons, the cosmic microwave background photons, are going to interact and pick up signatures, right? And so that's one of the main areas that I focused on in my research, and particularly with many collaborators here, including Alex Van Engelen, for example. And we'll see some of the work that we've done together here. Okay, so given that big picture view of what different epochs, different parts of the electromagnetic spectrum are probing in terms of epochs of the universe, let me just come back to this way of thinking about this endeavor as a way to make predictions that you test with other experiments. So one remarkable fact about the way we study cosmology is that you can start with extremely simple beginnings. So if you have, in particular, an inflationary epoch, a period during which you have exponential expansion of the universe, then tiny quantum fluctuations in that in the early universe fields get eventually amplified to form the structure. And the spectrum of those fluctuations, the experiments that we conduct today are consistent with the fact that they have a very simple spectrum. And by spectrum, I mean this. And you're going to see plots like this very often in this talk. So let me just try to repeat this a couple of times. You're going to see an amplitude as a function of wave number of some sort. Okay, so this is essentially saying that the initial random field that the universe started out with has essentially a scale invariant spectrum, right? Except that it has a slight tilt. So that tilt that's slightly different from 1 is captured in this NS number. And the amplitude of the fluctuations itself, how large the fluctuations are, is captured in this AS number, the amplitude of scalar fluctuations. So those are two free parameters in the model. We often test extensions of those models. But again, everything that we're predicting in the late universe starts from these simple beginnings. You have essentially a static field, essentially white noise. And those fluctuations then grow under gravity to form the structures that we see later today. Okay, so let's move ahead a little bit forward, right? And then once you start including the different ingredients in the cosmic soup that include photons or radiation, baryons or ordinary matter, mostly protons and electrons, and neutrons. And then dark matter, which I'll talk about in a little bit. It's a crucial part of the soup. It's some kind of particle that doesn't interact with other particles other than through gravity. When you put these ingredients together, you get really interesting physics, right? So you have oscillations in that primordial plasma where the baryons are falling in the gravitational wells that are produced by the dark matter, which is 80% of the matter. And then the radiation pressure pushes it back, and you just have this plasma that's sloshing around, right? So essentially in that early universe plasma, you have sound waves that are propagating in the early universe. But once the plasma turns into a transparent neutral hydrogen phase, those photons are no longer interacting with the baryons. and you get a snapshot. The sound waves get frozen. And when you look at a spectrum, when you look at the fluctuations in that map, you find that there is a key signature, key evidence for the Big Bang model, right? That you have these acoustic oscillations where the first mode that you're measuring here is essentially telling you the size of the sound horizon, or the distance that a sound wave in the early universe travels since the beginning of the Big Bang. And then you have additional oscillations. There's a fundamental modes, multiples of the fundamental mode in those oscillations. So since dark matter is a really important ingredient here, let me just again remind you why we think it's there and why we think it's one of the key open problems to address. So these are pictures from computer simulations that show how structure forms when you have a mix of 80% dark matter and around 15% of the total matter being baryons or ordinary matter. So in the zoom in, you have the baryons, but most of the matter that you need in order to explain the structure that you see in the universe is dark matter, right? And it is a key aspect of it is that it has no interaction with the baryons itself other than through gravity. And it's also important for the dark matter particles to be essentially cold and have a low velocity dispersion, basically collisionless, because if they had too much of a velocity dispersion, they wouldn't cluster the way that we see in these simulations, right? If things are moving too fast, then you don't form the deep gravitational wells in order to form stars and galaxies and clusters later on in the universe. Okay, so the model that we end up with is that these galaxies are embedded in dark matter halos. And the dark matter particle, some unknown substance that we're trying to figure out what it is, has to have a low velocity dispersion, deep gravitational wells. Cold dark matter makes up 85% of the mass in the universe, but only a third of the entire energy density in the universe. And dark energy is an entire topic which I won't go into in too much detail later on, but the rest of the energy density in the universe is consistent with something that is smooth and constant in time and causes the expansion of the universe to accelerate in the last few billion years. Okay, so this is the model, right? And the idea is that when you observe the anisotropies, the fluctuations that are essentially the mix of sound waves that are frozen from that primordial plasma, that model, the lambda CDM model, has only 6 parameters essentially. First is the fraction of matter, the fraction of the energy density that is in matter, that is not dark energy, for example. The fraction that's in baryons is ordinary matter, that's around 5%. Mega matter is around 0.3. Then you have the two numbers describing the initial fluctuations in the universe. And you have the Hubble constant, which you can think of as the expansion rate today. You can think of it as the inverse of the age of the universe. It's setting the clock for when you make the measurement itself. And finally, there's a nuisance parameter, which is the optical depth to reionization. So those CMB photons that have been traveling because the universe became transparent, but remember the universe reionized later on, which means that there's a small probability that those photons will have scattered since then. It's around 6%, 6 to 9%, depending on which measurement you look at. So that's a nuisance parameter, and you have to marginalize over it. And essentially, this is the only parameter that is not somehow related to maybe some kind of fundamental physics here, right? So it's incredible that with that 6-parameter model, you can fit not just the temperature anisotropies itself, right? There's lots of data points here. You can also fit the polarization. The CMB photons itself get polarized because the Thomson scattered off in the early primordial plasma. So I'm not showing that spectrum here. I'll show that in a bit. But that 6-parameter model is an incredible fit to the CMB data. So the idea here is to build this standard model and essentially measure it using the early universe measurement of the cosmic microwave background. Okay, so just spending another minute on these kind of plots, because if you haven't seen these kinds of plots before, the amplitude of the fluctuations that you see in this map, this oval here is the entire sky as mapped by the Planck satellite experiment, and which ran from around 2009 to 2013. And these are the acoustic oscillations that show as a function. So you go to the right, these are smaller scales or higher multipole moments. Just a really quick recap here, right? I mean, if you're looking at, you usually talk about these L modes, and that's just a spherical harmonic decomposition of this Gaussian random field, right? And as you know from spherical harmonics, the L is equal to 0 is the mean of the map itself. And as you go to higher multipoles, you start probing smaller scales. So one way to see this is that if this is your map, this is a simulated map, and now in a cylindrical projection, and this is your spectrum. The fact that this spectrum has this shape is essentially telling you that there's some amount of power on the largest scales, and as you go to the scales that are dominated, essentially that the scale that corresponds to the size of the sound horizon itself, right? The scale set by the sound horizon at the recombination epoch is where the power peaks. And so you measure the distance to the sound horizon really well, and so you have lots of power amplitude in this map. And as you go to smaller scales, an effect called silk damping will wash out those small scales, essentially. Okay, so that's how you want to think about these plots of the amplitude versus fluctuations. It's just telling you how much power there is in the map on different scales. Okay, so I spent first 15, 20 minutes setting that background, but the test that we want to do, and this is the thing that is really opened up by more recent experiments since Planck, together with large-scale structure, is to take that beautiful model that's been fit and then propagate it forward in time. Don't just stick to 380,000 years after the Big Bang, go all the way 12 billion years into the future. And if you think about it, that's a highly non-trivial thing, right? You're measuring something at 380,000 years, and you're going to say, I'm going to predict what stuff looks like 12 billion years later. And it better be right. So it turns out that on large scales, you can do most of these calculations for how gravity causes dark matter fluctuations to evolve with linear theory, right? And if you stick to these linear scales, it is not a foolhardy endeavor to try and predict what the spectrum of the matter fluctuations itself should look like. So now we're asking the question, not what the radiation anisotropies look like, but how does the dark matter dominated structure in the universe, what does that look like as a function of scale? And this is a prediction that you can just run with a numerical code that uses linear theory and predicts what the size of dark matter blobs should be late in the universe as the structure has evolved over time. By the way, I forgot to mention that very happy to take questions at any point. And if anything, if you want to interrupt and ask a question, please feel free to do that if something is unclear. Yes, please.
So, what's the scale of that picture, like the typical radius of one of those voids or the length on that ranking?
Yeah, that's a really good question. So the final map that I'm showing here is at very low redshifts. It's today, essentially, right? And at this point, so this is a bit misleading. So this is the linear matter power spectrum. This is the matter power spectrum today when things have gone very nonlinear. In particular, the biggest knots that you see here are virialized objects. They're galaxy clusters, right? So there's a typical virial radius that halos form. The other structures like the filaments are harder to predict with impossible to predict with linear theory, essentially. So I don't have a quick answer to that question. But so we don't try to use these super nonlinear scales and low redshifts. If you imagine kind of blurring this map and just thinking about the linear scales and you don't really see the filaments, that's where you want to be where things are analytic. That's a good question. Okay, so let me introduce another number here. So you take this power spectrum, which tells you the amplitude as a function of scale, which you can kind of think as a scale-dependent variance in the field, right? And if you think of a random field like this, one way to compress the information into that is to ask the question, what is the variance of that field? Right, to give you a random field, how much is it fluctuating? What is the dispersion in that field? Okay, and that's essentially what the sigma 8 number is. You can kind of ignore the 8 and just think of it as the variance. The sigma 8 square is a sum over the power spectrum that tells you what the variance in that matter density field is. And P of K is the power in the matter density field. So you can make a prediction, if you stick to linear scales, of what that variance should be. given the model that you fit over here. Some experiments don't directly measure sigma 8, which is the standard deviation of the field, but they measure a combination together with the total matter density in the universe. So I'll often talk about S8 as well, right? So this is the name of the game, right? At least this part of cosmology, right? One thing you can do is ask the question, is the early universe prediction for sigma 8 consistent with the direct measurement? Now you can go to the late universe and start to look at things like counting galaxies or looking at the shapes of galaxies. In fact, that's one of the main ways in which the variance in the dark matter density field has been measured, is to look at gravitational lensing. Now, why is that? Well, most of the matter is dark. You can't actually see it, right? So you need some way to see it and measure it. Even if dark matter does not interact with baryons, it's going to affect the gravitational potential, and that bends light. So the path of photons is going to be affected by the dark matter. So even if you can't see it literally, you can see it in the distortions of background sources. So this is an extreme example of a galaxy cluster causing extremely strong lensing. But at a statistical level, what you can take is you can take a distribution of galaxies that have, let's say, that are perfectly circular. If you put a dark matter lens, then they're going to be distorted, and you can figure out statistically that there is a dark matter blob over here. In practice, with shape noise, the fact that galaxies have elliptical shapes is a little bit harder. But this is one of the main ways in which experiments like the Dark Energy Survey, KIDS or HSC or the future Rubin LSST telescope is going to be measuring this parameter, sigma 8, is to infer the presence of dark matter across the sky by looking at the distortions of the shapes of galaxies. And then once you've made that map of the distribution of dark matter, it's really the dark matter plus the baryons, but the baryons are just 15%, so I'm just going to loosely call it dark matter. Once you do that, then you can calculate the amplitude of that field, and then you can ask the question, is that amplitude consistent with the early universe? But we, today, are going to be using gravitational lensing of the cosmic microwave background itself, right? This is what I've spent a lot of my time on, again, with collaborators here. So the main workhorse for this in the last 10 years, for me at least, has been the Atacama Cosmology Telescope. So this is a ground-based telescope, which means you can make your mirrors large and you can have a higher angular resolution, which is going to be really important. Okay, so it's in a high and dry place in the Atacama Desert, or at least it was decommissioned in 2022. And the ACT collaboration is a large collaboration, 160 people at many different institutions. This is one of the last photographs we took in terms of collaboration meetings. What does the sky look like when you look at it with a telescope like the Atacama Cosmology Telescope? So if you're used to seeing pictures of the cosmic microwave background, this diffuse field, that's a picture of the snapshot of the early universe. This is what it looks like when you have the Planck satellite experiment, for example. Satellite experiment, it's small, its angular resolution is small, so things look a little bit blurred when you zoom in. But once you switch to ACT, you start to see more small scale structure here. My collaborator Sigurd Ness has a really nice way of plotting these maps, which is that the cosmic microwave background is supposed to have a black body spectrum. The universe is in thermal equilibrium early on, so it has a very nice Planckian spectrum. So if you divide out that spectrum and if you combine multiple frequencies, at a 90, 150, and 220 gigahertz, which is where we mostly make our observations, we expect the CMB to have the same amplitude, okay? Because we're normalizing out the Planckian or black body spectrum. So that means if you make this composite false color map, the CMB looks kind of boring there because it looks gray, right? It has equal amplitude in these three different frequencies. But things that have a falling spectrum, like synchrotron sources, active galactic nuclei that are essentially supermassive black holes at the centers of them, they look orange. And things that have a rising spectrum, these are dusty sources, nearby spiral galaxies will look blue. Okay, so if you take that diffuse CMB background and you ask the question, how do current generation experiments improve beyond what Planck has already done? This plot kind of shows you that. The blue points here are the Planck satellite experiments measurements of the acoustic oscillations. These oscillations in the temperature spectrum are what I showed earlier. As I mentioned, there's also a signal in the polarization, which is completely consistent in this lambda CDM model, right? Which is, again, an incredible thing. This is a 6-parameter model. And what you fit to the temperature data can predict what you see in the polarization data itself. There's a big program to look for B mode type polarization, which I won't go into, but that's B modes are expected to be produced by primordial gravitational waves in the very early universe. There is also a B mode signal that's produced by gravitational lensing itself, which is what you're mostly seeing here. But the reason we make these B mode plots is that to someday be able to detect the signature of primordial gravitational waves, topic of another talk. But the main point here is that ACT and SPT, we're making precise measurements of these acoustic oscillations to higher precision than Planck. And if you look at these experiments independently, this is a data release that we had just last year, our final data release from the ACT experiment. You can see that our posterior constraints on the different cosmological parameters or derivatives of those parameters, including the age of the universe, they're all very consistent between Planck, ACT, and SPT. And this SPT measurement here is also from last summer, is a pretty recent one. So looking at the early universe fluctuations itself, the early universe parameters, consistency between different experiments, and that's important. And I'll just spend one slide on this. If you've heard of the Hubble tension, this is, so you can, one of the things you can predict from the early universe CMB measurements is the expansion rate of the universe today. And there's a little bit of a debate or controversy around this today, which is the fact that if you try to use direct measurements of the expansion rate today by looking at exploding stars, supernovae, and how their brightness changes over distance, you find a higher value with certain ways of calibrating those measurements, whereas other ways of calibrating those measurements lie somewhere in the middle. And so one of the things you can do with cosmic microwave background experiments is to make the early universe prediction, which again lies in tension with this, with the Schu's method of measuring the current expansion rate today. But once you have lots of precise data in temperature and polarization, you can start opening up your model and saying maybe something weird happened early in the universe, maybe had an early dark energy, or you have interacting neutrinos, or maybe late in the universe something weird happened. You can open up your model beyond lambda CDM and ask the question, does it resolve the tension? And the answer is no, right? You might push things out to maybe a 70 kilometers per second per megaparsec, but it doesn't really resolve the tension. Okay, so that was all to say that current generation CMB experiments have a consistent view of the early universe with what Planck saw. I want to talk about what those experiments like ACT and SPT are going to tell you about the late time effects and show you that we can make a direct measurement of the amplitude of dark matter itself with the same CMB experiment itself. So once you look closely at these maps, there's the diffuse early universe background, and then there's these quasars, and then there's dusty galaxies. So these high resolution experiments like ACT open up your sensitivity to late time effects. My favorite thing is the thing you can't see here, but is shown here is the arc-minute scale deflections due to the structure in the universe itself. The gravitational potentials in the late universe will cause those CMB photons to go through different paths. So let me talk about that a little bit. If you take the cosmic microwave background, you put it out all the way over there, and you're over here, then those CMB photons are going to be traveling through the universe, which has become transparent, mostly transparent. And as time evolves, those initial fluctuations in the early universe are going to grow with gravity, and the dark matter fluctuations are going to grow, and they're going to form structures. And as those structures form, the CMB photons are going to get more and more deflected in the gravitational potentials of those structures. So a really great thing is that the distance to the CMB itself is known very well. And the epochs that are probed by the CMB lensing signal, the deflections in the CMB itself, are very well described by linear theory again. Okay, so if you can measure that gravitational lensing signal, then you can really access information about the way dark matter changes over cosmic time late in the universe. So now you're going beyond just the early universe snapshot. There's just a little quick math here, right? So the distance to the last scattering surface, which is the cosmic microwave background, is around 14,000 megaparsecs. And the typical size of large blobs of dark matter along the line of sight is around 300 megaparsecs. So these cosmic, the CMB photons are going to encounter around 50 deflections in these large potential wells. And we know from linear theory that the size of the deflections are set Well, Einstein's theory just tells you that the size of the deflections is set by the gravitational potential. If you have a smooth gravitational potential, you don't see any deflection. But if you have fluctuations at the level of 10 to the minus 5, which is what's predicted based on what we see in the CMB, then you get angular fluctuations that are of the order 10 to the minus 4 radians. And these photons are then doing a little random walk where they do 50 deflections with that angle. So the RMS fluctuation, the deflection angle, is around square root of the number of deflections times the typical deflection, which ends up being around an arc minute. Okay, so an arc minute is 1/60th of a degree. So a degree is what if you hold your hand out at arm's length, it's going to be a degree and divided by 60. So that's roughly the resolution you need in order to really measure the signal really well. Okay, so a little simulation to show you how that looks. A blink between the lensed and the unlensed CMB shows you that you can kind of see that there are tiny deflections that are arc minute size, but those deflections are coherent over degree scales because the degree scale is roughly the size of the dark matter blob projected along the line of sight. Okay, so you can write the lensed CMB as being a remapping of the unlensed CMB by the gradient of the potential itself integrated on the line of sight. So if you're able to extract that signal, you're measuring the gravitational potential integrated along the line of sight. Just one slide on roughly the algorithm that we use in order to extract the signal. So if you take quadratic combinations of the CMB temperature map itself, then you can weight them in such a way that you isolate the potential. So that's a lot of words, but in pictures, an approximate explanation is the following. We expect an unlensed CMB to have an angular power spectrum. Its distribution as the size of the blobs as a function of scale to have a certain spectrum. But if you put a dark matter blob over here, you're going to magnify that particular region of the CMB, which is going to cause you to shift power to larger angular scales. So locally, if you have a dark matter blob in this direction, the power spectrum in this location is going to get shifted to the left. If you have an underdensity, then you demagnify and you're going to shift the power to the right. Okay, so essentially what these kind of quadratic estimators do is they tell you how the power spectrum changes as a function of position on the sky, which allows you to mode by mode. L is a Wade number of a 2D map. Mode by mode, reconstruct the dark matter dominated potential itself. So what you can do is you can take the observed CMB microwave light. There's, again, 20 years of algorithm development that goes into this, including dealing with astrophysical foregrounds, which I don't have the time to spend in this talk. That takes you from these maps of the cosmic microwave background to maps of the gravitational potential, which is sourced by the total matter, which is dominated by the dark matter. Okay, so again, taking a step back, this is incredibly cool, right? You can take a picture of the CMB and you can tell where there's more dark matter and where there's less dark matter. Because you can't directly see dark matter, but you can see it through its gravitational effect. And crucially, you need high resolution to do this. This is why an experiment like ACT or SPT or the Simons Observatory is really good, because we have mirrors that are the size that can resolve arc minute scales. Right? So this is, again, just bringing back that point that we need these high resolution experiments to really make use of this effect. So this is from a paper that I led with collaborators here, including Alex, that did this on one of the final data sets from the ACT experiment. So we take the CMB maps that are produced by ACT over a third of the sky, and then you transform it with this quadratic estimator pipeline to make a map. This is the sphere, the sky that you see. And this is plotted in units of gravitational lensing convergence, which essentially is the projected mass density. Okay, it's a 2D mass density. This is what you want to think of this as. It's the Laplacian of the potential. And you might think this is just a map, but you can kind of already see that this makes physical sense in the sense that I'm going to claim that you can actually see the dark matter distribution here, dark matter dominated total matter distribution by I. The typical size of the lumps here is around a degree scale, which corresponds to the peak of the matter power spectrum that I showed you earlier. And that peak is set by, again, linear physics that tells you the essentially the scale set by the matter radiation equality epoch. So it's very easy to predict that. But that peak is essentially where you see the typical lumps in this, right? So that's one way to maybe tell yourself that you see dark matter dominated structures here. But if you want to really convince yourself, what you want to do is you essentially want to do a cross correlation. Now this is a zoomed in view of the map itself, now plotted in units of gravitational potential rather than convergence. And again, you see these dark spots are the underdensities in the dark matter dominated distribution, and the white spots are the overdensities. But on top of that, I can overplot a distribution that is calculated from some other source. For example, early in the universe, star formation peaks at some point, at some age, at some epoch of the universe. And you have lots of dusty star-forming galaxies. So you can take a sample of dusty star-forming galaxies. You can take the distribution of those dusty star-forming galaxies, and you can ask, what does the distribution look like when plotted against the CMB lensing inferred gravitational potential? So when you do that, you see this plot, where the blue are the underdensities in that galaxy distribution at high redshifts, and the reds are the overdensities. And you see an excellent correspondence between the two, as you can see here. The overdensities in the galaxy distribution from early times corresponds very well with the overdensities of the gravitational lensing itself. Okay, so this is really convincing you that hopefully convincing you that this is really mapping out the dark matter dominated structures at a certain epoch. Okay, so the reason we're doing all of this is to ask the question, what is the variance of this map? Okay, so going back to that story of predicting what happens late in the universe, you have a standard model that's calibrated off of measurements of the early universe cosmic microwave background. And then you try to predict the variance in the dark matter field later on, sigma 8 or S8, which is just looking at the variance of this map. But of course, there's subtleties in doing that. But once you do that, the reason we do this is because the indirect prediction in green from just looking at the early universe fluctuations is shown out here. It's S8 of around 0.85. What we find is that with these dark matter maps that are inferred using CMB lensing, CMB gravitational lensing, we find an answer that is consistent with the early universe prediction itself. This is a slightly older plot. It's from my paper from a few years ago. And it shows many measurements, some of which are correlated, essentially, so you can't draw too much from this. Some of these measurements that look at the distortions of the shapes of galaxies using galaxy weak lensing, they tend to be low. And there are other methods, such as using the clustering of galaxies itself, or cross correlations of CMB lensing with low redshift galaxies. So some of these tend to lie a little bit low, maybe 7 to 10% low. And this is where people have talked about this thing called the S8 tension. Since then, the kids measurement here, since we put out this paper, the kids measurement has come out to be a little bit higher in reanalysis. And there's a more recent dark energy survey measurement that has also gone slightly higher, but with a smaller error bar. So it's questionable whether there is a tension. Maybe there is, and maybe it's not as large as this plot makes it look. So if there is a tension, then we have to ask the question, how do we resolve it, right? So why do the predictions of the early universe match when we use the CMB lensing technique, but not necessarily completely precisely match when we use more recent epochs of the universe and different techniques? Okay, so I want to spend a little bit of time talking about how the community is trying to address this question. And in this plot, what you see here is on the y-axis is the scale factor, which is the factor by which the universe has expanded. So 1 is today. Redshift is on the same scale here. Redshift is 0 today. And so if you go down on this plot, you're going to earlier times. If you go left and right on this plot, you're talking about different wave numbers. So the largest scales in the universe are out here, and the smallest scales in the universe are out here. So one way to think about the variance tension, the sigma 8 tension, is that different probes of the universe, of the structure of the universe, a call from Italy, are probing different epochs in time on the y-axis and different scales of the fluctuations itself. Okay, so if there is a tension, then we need to understand which parts, which epochs in time and which scales are causing that tension. So the CMB lensing measurement here is probing relatively intermediate scales, relatively intermediate epochs in time, and large scales, linear scales in the universe. That's the phi measurement here. The early universe primary CMB anisotropies, the thing that makes the prediction itself, is probing extremely early times and extremely linear scales, whereas these gamma measurements, which are the cosmic shear measurements, the galaxy distortion measurements, are probing both late times and small scales in the universe. Okay, so rather than just talk about the sigma 8 number, what we have to do is try and disentangle cosmic evolution and scale evolution of the fluctuations. That's one of the programs that's being that the community is undertaking right now. So let me pause quickly for questions before I go forward, because the next parts are, yes.
CMB as it was emitted versus
Yeah.
from the pathway that it follows to your in the dark matter. How do you, are they different size scales, or do you have some way of obtaining them?
Very good. Okay, so in this plot, so essentially, the idea is in this picture here, which is that the statement is statistical isotropy. So if you have no gravitational lensing, you have statistical isotropy, which means that the power spectrum, angular power spectrum on this part of the sky should be the same as the angular power spectrum on this part of the sky. Okay, so if you have a dark matter blob here and an underdensity here, then you break statistical isotropy. The power spectrum here, it might be shifted to the right, power spectrum here might be shifted to the left, right? So that immediately tells you that there's a way to disentangle the change in the dark matter density across the sky, but not necessarily the amplitude itself, right? So that has to be inferred from the power spectrum, or the average power spectrum of the entire sky itself. So you can normalize the dark matter density by looking at the average power spectrum of the entire sky, which we measure extremely precisely well.
That you expect to be emitted and that you can measure, if there is a significant variation in the CMB that's at the same size scale as the lumps that you're looking at.
Oh, right. Okay. Yeah. So this gets a little. So the scales that let you map out the large scale distribution of the dark matter itself are the Archimedes scales in the CMB, right? But these are degree scales. Very good question, right? So if anything that's funny on the very largest scales in the universe, like galactic dust emission, for example, which might be a foreground, doesn't even enter in your estimator because it's downweighted, because the information is in the small scales. Very good question. All right. Any other questions? Yes, Alex.
Back to your case.
Yeah. I believe that's cluster abundance. Yeah, so you can count the number of galaxy clusters you see. It's a little trickier to do this with controller systematics, but yeah, it probes still kind of linear scales in very late times, right? Okay, so my group has been trying to push on this question, essentially trying to disentangle the scale versus the cosmic time. So one of the ways in which you can do this very effectively is to remember again that the gravitational lensing signal from the CMB is integrated along the line of sight, integrated along time, cosmic time, which means that if you have a sample of galaxies in this slice and a different sample of galaxies in this slice, then you can cross-correlate your CMB lensing map with the different samples. So if you know the redshift, if you know the distance distribution of those galaxies, then you can see how that time evolution behaves. And so this is what my student Joshua Kim did, which is he took samples of galaxies from the dark energy spectroscopic instrument, these DESI galaxies, and he asked the question, what is the amplitude of fluctuations as a function of redshift, where each of these data points is coming from a distribution of galaxies that we know are at a certain distance. So Z, you can kind of think of as distance, as a redshift, or you can think of it as cosmic time, right? So out here on the right of the y-axis is 6 billion years, left here is 9 billion years. So there's a time evolution of the variance of the dark matter density field itself. I'll give you like a few seconds to think about why that might be the case. The variance of the dark matter field itself increases with time as you get to lower, more recent epochs. Because again, this is because structure is evolving. Things are growing under gravity. So the variance should increase with time, which is what we see. The blue data points are what Joshua measured. And it's a little bit inconsistent with the CMB prediction, but only at the 2 sigma level. And so together with our collaborators, Noah Saylor and others, we did a much larger sample of galaxies that go out to even lower redshifts or more recent times, right? And this is where the 12 billion year in my title slide comes in, that if you go to these final bins that we measured here, these go to very recent epochs that are measuring 12 billion years since the Big Bang. And when you put all of that together, okay, the time evolution is not that weird. Okay, so now you're taking the CMB lensing map and you cross-correlate it with galaxy distribution, and you see that there is this nice evolution that kind of scatters around. If you put all of these different measures together, it isn't really inconsistent with the Planck plus ACT primary CMB early universe prediction. Okay, so then we try to understand whether there's a scale problem here. So another problem that you can have is that maybe, if you go back to this plot, maybe it's not that there is some non-trivial time evolution in the physics, but maybe when you go to super nonlinear scales, which is what many of these galaxy weak lensing measurements tend to do, they have to, because they're mostly measuring more recent things, the scales that they have access to have gone nonlinear pretty fast, right? And so you're mostly in this nonlinear regime. And when you get to the nonlinear regime, you have clusters that virialize and you have structures that form, but more importantly, the baryons, the ordinary matter in the gravitational potential wells could be doing things that affect you on those scales. Okay, so one of the things that can happen is that you might have active galaxies, essentially quasars, that have supermassive black holes that are creating gas around them, and then they push that gas out. Now, gas is only 15% of the total matter distribution. But when you get to smaller scales, you can have a 15% effect on your prediction for what the power spectrum of matter should look like. How do the fluctuations look like? So you might have a suppression in particular. If you push out gas, then you're going to make things more puffy on those scales. And that can have a slight feedback effect on the dark matter itself. The dark matter is going to now respond to the new gravitational potential that's 15% different set by the baryons. This is really messy stuff, right? It's really hard to simulate what baryons are going to be doing, what active galaxies are going to be doing. And this is a whole different set of hydrodynamic simulations that look at the effect of baryons. They have different subgrid physics going into them. And you see that they all make very different predictions, right? And so you don't really know what's true. Importantly, the scales that are probed by CMB lensing, where sigma 8 or the variance is consistent with the early universe prediction, is very much not affected by this baryon feedback. The effect is extremely small. Our galaxy lensing is significantly affected because it's probing things that are on smaller scales that are more affected by baryons. So this is why people have been interested in the question of baryonic feedback, is because this could be a possible resolution to that 7 to 10% difference in the variance that's measured by CMB lensing and the variance that's measured by galaxy lensing. So one of the things well, another reason why this is interesting is if you, apart from messy astrophysics, another thing that could cause a suppression in the matter's power spectrum is if you have non-trivial dark matter. If you have a non-trivial dark matter that it's not just some boring cold dark matter model. I have one slide on this soon, but I just wanted to anticipate it. If you have axion dark matter, which has a very large de Broglie wavelength, then it can effectively behave as a quantum mechanical object on galactic scales, which suppresses the power spectrum of the matter field on scales that are around this scale, right? So it is interesting to look at those scales because you may be able to test things like the particle nature of dark matter, but at the same time, you have all this messy astrophysics getting into the way. So my student Karen did a really nice analysis, Karen Perez-Sarmiento, where she combined the ACT CMB lensing measurement with the DES galaxy lensing measurement to ask the question, what is the shape of the matter power spectrum when you do a joint fit of two of these experiments? And indeed, you find that you have this kind of suppression. the purple to green points here are different models for baryonic feedback. The dashed line here is the prediction if you have axion dark matter, which my postdoc Alex Lagu is very interested in. Is the main thing he wants to be able to learn about is whether axion dark matter is a true explanation for the particle nature of dark matter. So they worked together and had competing explanations for what could be causing the suppression. And what we conclude from this is that if you just take joint measurements of CMB lensing and DES weak lensing, yeah, you see a bit of a suppression of that matter power spectrum, which is interesting, but you can't tell apart baryonic feedback, messy astrophysics, from interesting new particle dark matter. Okay, so Alex got obsessed with this question and wanted to figure out a way to get around this. And so one path towards this, which I'm sketching the last 5 minutes, is that if you look at hydrodynamic simulations, then the change in the matter power spectrum in these hydrodynamic simulations with respect to the dark matter only simulations, which are easy to simulate, this is the suppression in the matter power spectrum, it's found that it is a very strong function of the gas fraction in halos of a certain mass. Okay, so if you have more gas left in the halo itself, that's evidence that feedback has not pushed that stuff out, which means that the suppression in the matter power spectrum is essentially zero. But if you have very little gas left in the halos that you look at, so this is a paper from Van Dalen et al. A few years ago that motivated our study. If you have very little gas left, then that's telling you that the suppression in the matter power spectrum should be very small. So what this is telling you, there's some way of accessing the gas fraction in halos of 10 to the 13 or 10 to the 14 solar masses, then that's going to tell you what the matter power spectrum suppression should be, so then you can pick out which of these baryonic feedback models it is, and then start to constrain the particle nature of dark matter. So one really exciting way to do this, again, with the CMB itself, and I'm going to be very fast here because we only have a few minutes left, is to use another scattering effect in the CMB. It's called the kinetic Sunyaev-Zeldovich effect. So this is essentially the Doppler shift of CMB photons as they scatter off of free electron clouds late in the universe. So remember, the universe is reionized. So if you look at a halo of matter that's virialized, it's going to have a bunch of free electrons in it. And the CMB photon is going to scatter off of it. But if that halo is moving, then you pick up an extra Doppler shift, which shows up as this particular secondary anisotropy in the CMB itself. If you look at the CMB, which has typical fluctuations of around 300 microkelvin, then these kinetic SC or KSC fluctuations are extremely tiny. They're a few microkelvin. And so these little speckles here that you see are halos late in the universe. And whether they're moving towards you or away from you, you're going to have a certain sign change in the CMB itself. So a few years ago, with collaborators, I've thought about many different ways of extracting that signal very efficiently. One cartoon way of thinking about this is that if you have this cosmic velocity mode where the things are moving towards or away from you, then the way that the CMB map should look like due to the KSE effect, this is all highly exaggerated. You don't see this effect by eye. If you have certain galaxy positions, is that you would see that when things are moving away from you, things look colder, and when things are moving away from you, things look hotter, right? So you can write specific estimators in order to extract the signal. These kinds of estimated kinds of measurements have been done by many different groups that look at the effectively the size of the KSE effect as a function of scale away from the center of the halos that you're stacking on. Right? And in all of these cases, you do see that the prediction from dark matter only simulations, which is often called NFW on these plots, gas traces the dark matter in solid lines, is not actually what's measured by the KSE measurements. You see more suppression. So this is a young field. Okay, so these measurements have only been made at the 10 sigma level. But in the next few years, with the Simons Observatory, which is going to be the subject of the last few minutes, this signal, the KSE signal, is going to be measured very well. It responds directly to the gas distribution itself. Okay, so given what I showed earlier, if you can measure the gas distribution, then you can predict what the matter power spectrum suppression should be. And so now you can disentangle these late time effects. So what Alex worked on was to go into these hydrodynamic simulations and ask a similar question. How does the matter power spectrum suppression due to baryons behave as a function of the strength of the KSE signal itself? Okay, so he saw that there is a correlation between those. And then he built an emulator that it's a data-driven emulator that accepts as inputs the measurements that you make with a CMB experiment in cross-correlation with galaxies, the KSE effect, and transforms that into a prediction for what the matter power spectrum should be. And there's more tests, or leave one out tests in this paper that look at what happens if you don't train with certain models. The emulator works really well and gives you sub% scatter on that power spectrum measurement. So just as a prediction for the future, right? So if you use future measurements of the KSE effect, then you can predict with low error bars what the power spectrum suppression should be. And this Alex is very excited about this because he wants to then disentangle the effect of baryonic feedback and then actually put constraints on the particle nature of dark matter. Okay, so with that, in the last couple of minutes, I just want to, so even though many of these measurements that I've shown are from the Atacama Cosmology Telescope, which has been decommissioned, the question is, how do we push these new methods forward? And one particular way that I'm very excited about is the Simons Observatory. So this is an experiment that is looking at the millimeter sky, again, in more frequency bands than ACT has looked at. And it's looking at the same resolution, but much higher sensitivity. So a little status update, right? So in February 2025 last year, we had first light. We looked at Mars. It looks nice and round, which is what you want. So that's great. And then we completed commissioning of the telescope earlier last year. And then we went through we are going through a period of initial science observations where we do, some targeted observations. And I want to stress that this is done at 5 times the mapping speed of ACT, which means you have 5 times the number of detectors. So what took us 5 years to do with ACT would take us 1 year with this particular version of the Simons Observatory. As we speak, the Simons Observatory is being upgraded. Right, so even though we spent less than a year with the initial Simons Observatory, the nominal Simons Observatory, it's been upgraded to have twice the number of detectors. So once we start back up, hopefully pretty soon, we'll have 10 times the number of detectors that ACT did, which means we'll have 10 times the mapping speed of ACT. But just to show you what some of these things look like, well, first of all, we cover a very good fraction of the sky that has lots of overlap with galaxy surveys like LSST and DESI, which means we can do a lot of these cross-correlation analyses that I mentioned earlier. Here's a map from ACT that took 5 years to make. And here's a map from the Simons Observatory that took 144 hours to make. And you're supposed to be impressed by the correspondence between the very large blobs here, okay? So you can see some correspondence between the large blobs, and that's because the CMB that you see shouldn't have changed in the years since ACT and SO, right? But it's not perfect correspondence because you have noise, and we have to beat down that noise. Again, stressing this is 5 years of ACT versus 144 hours of SO. And we're a very eager bunch, right? And so we have all of our pipelines ready that we've learned the lessons from ACT to run it all the way forward into science. So even with the small data set, we've been doing things like measuring the acoustic oscillations, the temperature power spectrum itself. This is with 60 hours of data. You can see clearly the acoustic oscillations. You can even see it in polarization, right? So that's a harder measurement. You need lower noise. 60 hours of data, you see the acoustic oscillations in the polarization. We went even farther than that to working in the lensing working group. For example, Karen made this gravitational lensing map of a small patch of the sky with a bunch of collaborators, including Alex here. And this is, again, a preliminary measurement that shows, again, you can overlay the cosmic infrared background and you see some correspondence, but not the perfect correspondence you saw before. Again, this is only 144 hours of observation. So with 144 hours of observation, you can make dark matter dominated maps, right? So it's pretty incredible. And you can see that cross-correlation done, again, as a function at scale. This is done by Ola Kosiak. You can see a clear detection of that cross-correlation between the CMB lensing map and the cosmic infrared background itself. And finally, I just want to quickly say that this is a very small fraction of the science that Simons Observatory will do. There's many, many, many different things that I haven't talked about, such as measuring the thermal synergy of Zeldovich effect, the large-scale B mode. So we have a set of small aperture telescopes that are looking for signatures of primordial gravitational waves. There's a huge amount of science that can be done with the Simons Observatory. It's very exciting to be a part of it. So I'll leave the slide for any last questions. Thank you.